Hello. This week I'm going to introduce you to the Fast Fourier Transform, or FFT, which is a streamlined version of the discrete Fourier Transform. The DFT is very useful, but it is very heavy on the calculations. Not a problem for a channel like this, which proposes the use of a slow, casual language like JavaScript to demonstrate these concepts, but very much a problem for serious signal processors who want to process audio signals in as close to real time as possible. Here's the formula for the discrete Fourier transform. If there are capital N samples in our time slot, given by lowercase f0, lowercase f1 and so on, then we calculate capital N Fourier values from them, which are the capital F0, capital F1 values on the left of the equation. Each Fourier value is a sum of capital N terms. I have laid out the calculations needed in a square grid below the formula. Imagine that list extending to capital N terms on each line and capital N lines down the screen. That basic formula is calculated capital N squared times. For each of the capital N k values, capital N terms are added together. If you double capital N, the number of calculations goes up by 4. We say that the discrete Fourier transform is of the order of n squared calculations, usually written as n squared within brackets, preceded by a capital O, as you see. Clearly we want to reduce this, and that's where the fast Fourier transform comes in. In fact, there are several algorithms for fast Fourier transform, each of which improves on the DFT in terms of how many calculations you have to perform. However, one of them, the first one in this list, the Cooley-Tukey algorithm, is almost always the one taught. It has become almost universal, to the extent that the others are just about eclipsed. Certainly Cooley-Tukey is the FFT algorithm that you will meet at university. In fact, it was only several years after leaving Durham University that I discovered that other versions of the FFT were available. I'll go through Cooley-Tukey here, of course. Why bother rocking the boat? If people are interested, then I might go through some of the others in a later video. For now, though, it will be Cooley-Tukey. And if you're anything like me, you have to think twice before saying the name. Like everyone else, I quite often find myself calling it the Cooley-Turkey algorithm by mistake. By using Cooley-Tukey, I'll try saying that 5 times quickly, we can reduce the order of the calculations from an order of n squared to an order of n log n, which is quite an improvement. Here's a list of terms in the summation written out for any particular value of k. However, I have grouped them into 2 columns for the even values of small n, 0, 2, 4, 6, etc., and the odd values of n, 1, 3, 5, 7, etc. What you see here is a generalization of the previous screen. Instead of little n as the counting variable on the summations, I have used little m, so that 2m is guaranteed to be an even number, and 2m plus 1 is guaranteed to be odd. The summation on the left uses 2m throughout and covers all the even terms in the original formula. The summation on the right uses 2m plus 1 throughout and covers the odd terms in the original. You'll notice that the upper limits on both those summations is half of what they were originally. This is because the counting values jump forward in steps of 2, so each one only needs half the number of steps. Instead of 1 less than n steps in one giant summation, we have 1 less than half of n in 2 summations. Of course, this assumes that capital N is an even number, and so far we haven't managed to reduce the number of calculations needed. Take a look at the odd part of the formula, specifically the plus 1 in the power. If you add something onto the power, that's equivalent to multiplying the base number by something. Here we can take out the plus 1 from the power as shown. Furthermore, since the term that we took out doesn't depend on m, we can take it outside the summation as well. Just add up the minimum necessary inside that summation that does involve m, and then multiply the whole result by that term afterwards. There is still k in that term that we've taken out, but that doesn't affect the summation at all. So when we clear away all the bodies and the dust has settled, this is what we're left with. Fk is defined in terms of 2 summations, both of which are very similar. Indeed, at first glance, those summations might look identical, but don't forget the +1 in the small f sample values, which I have highlighted in red. Oh, rats! If it weren't for that, we could calculate just one of them and use it twice. The even indexed half of the summation is generally referred to as EK. The odd indexed part, not including that term that has been taken out, as OK. Still, the two summations do have one term in common, and this can be calculated just once for every value of k and then reused. A computer program implemented to do this would go through the two loops simultaneously, calculate the term just once, multiply it by the appropriate sample value, and then add it to the appropriate running total. Now, so far, all we have done is increase the number of calculations we have to do. So much for the fast Fourier transform, eh? Well, here's where the magic happens. It can be shown that we can use the very same building blocks to calculate another Fourier transform value. The screen shows how we can calculate the Fourier transform values for the second half of the spectrum from the building blocks of the first half. It can be shown is academic speak for the maths is horrendous, don't even go there. If you want to go through it to prove it to yourself, be my guest. I ripped this off Wikipedia, so knock yourselves out. I want to keep this talk down to less than an hour, so can I ask you simply to take it on trust? This is the part of the algorithm that reduces the number of calculations. The two right-hand sides of those equations are identical, apart from a sign change, so we can calculate two Fourier values from the same four building blocks. Suppose capital N were 100, i.e. we had to calculate f0 to f99. If we knew E0 and O0, then we could calculate both f0 and f50. If we know E1 and O1, then we can calculate both f1 and f51, and so on. Now, if you've been introduced to the Fast Fourier Transform on your computer studies course, the chances are that you weren't taught any of that maths. Indeed, I bet they didn't even tell you that you had a choice when it came to picking your FFT in the first place. No, the first time you came across the Fast Fourier Transform, it was probably in the form of a diagram, like this. This, like the brain-bending maths you saw a moment ago, I ripped off Wikipedia, where they use small x to indicate the sample values and capital X to indicate the calculated Fourier values. The process works from left to right, with 8 sample values being used to calculate 8 Fourier transforms. The even indexed sample values go in at the top, the odd indexed ones at the bottom, and the Fourier calculations that you've just seen represented by those diagonal lines on the right. Those diagonal arrows are supposed to resemble a butterfly of some sort, so you might hear a diagram like this referred to as a butterfly diagram. Personally, I can't see it. The problem with this is that the whole thing is recursive. Those two large boxes in the middle are themselves Fourier calculations, with half the number of inputs of this whole one, in this case 4 inputs each. And so on, FFTs within FFTs, until you work your way down to 2 inputs each. The whole thing is more complicated than this diagram would have you believe, so we had better tackle it in a non-recursive way. The algorithm is usually demonstrated using a diagram like this. This example shows 8 sample values on the left, from which 8 Fourier values are calculated on the right, and you can think of those horizontal lines as representing time travelling from left to right. As far as I can tell, Cooley-Tukey always requires the number of samples to be a power of 2, and you'll see why in a moment. The example given is always for 8 sample values, as a diagram with 4 sample values wouldn't capture the complexity of the process, but if you increase the number of samples to 16, you end up with something as complicated as a London Underground map. So, 8 signal samples it is. I'm guessing you'd like a bit of explanation of that diagram. OK, look at the input samples on the left. You will notice that they're not in numerical order, nor is it simply a question of listing the even numbers first and then the odds. They have to be arranged in that specific order for the whole magic spell to work. While there are a few ways of calculating that order, here's probably the simplest way. Take each F index and write it in binary. Then reverse the binary digits to form a new binary number. Turn that number back into base 10, and that will give you the new order for the samples. Now for those diagonal lines. As I said before, They are called butterflies because they're supposed to look like butterflies. My old tutor at Durham University was of a different opinion. He told the students at the lecture, "Those things are called butterflies because they look like egg timers." I swear to God. Anyway, whatever you call them, each butterfly takes two inputs on the left, small a and small b, and produces two outputs on the right, capital A and capital B. They also need a value for k and a value for n. The literature refers to a letter W, or a Greek letter lowercase omega, which looks a bit like a W, as a shorthand for that expression involving e raised to the appropriate power. We specify a value for k and n, and the value of omega is calculated from it. Curiously, guides to the FFT often use lowercase n for that formula, which is confusing. I have stuck to capital N here to be consistent with all the formulae you've met up to now. The butterfly is basically an implementation of the equation you saw a few slides back with EK and OK, or rather an implementation of part of that equation. One butterfly won't give you the whole Fourier value, but the entire swarm of butterflies working together will. The two inputs take the place of the even and odd summations, and omega is the term that we multiply the odd summation by. The first stage involves performing the butterfly on adjacent pairs of input values. Think of this stage as four groups of two input lines in each group. The value of n, the lower index on the omega or w, is always the number of horizontal lines, the number of values from the previous stage, in each group. So n will be 2 for each of these butterflies. The value of k for each butterfly will start at 0 and climb up to 1 less than the value of n on the omega. Remember the limit of n minus 1 and all those summations that you saw? This works the same way. Well, since n is 2 here, the value of k for this first stage goes from 0 to 1. However, we don't need the value of 1, because in the range of integers up to 2, 1 is in the second half of that range, and we can use the omega value we've calculated for k equals 0 instead. That's why, in each of those butterflies, you should really see an omega value of 0, 2 for the top line, and an omega value of 1, 2 for the bottom. But we don't. Why calculate omega 1, 2 when we just take the value for omega 0, 2 and change the plus sign into a minus? Waste of time. For that reason, all the values of omega will be identical for this first stage. Now we move on to stage 2. The inputs to the butterflies are the output values produced by stage 1. This time there are two groups of 4 lines, and n is the number of lines in each group. So n will be 4. K will start at 0 and increase up to 1 less than n in each group. So k goes from 0 to 3. Except it doesn't. In the range of numbers 0 to 3, 0 and 1 are in the first half, and 2 and 3 are in the second half, and we don't need the second half. So k only takes the values of 0 and 1. To make things easier, I've colour-coded the butterflies so you can match them up to the omega values. And here we have the final stage, at least the final stage for this example. This group of butterflies covers all the horizontal value lines, all 8 of them. So the value of n will be 8. Now you can see why Cooley-Tukey is applied to time slots where the number of samples is a power of 2. All these groups of butterflies are based on powers of 2, with the size doubling at each stage. Apparently, it is possible to apply Cooley-Tukey to time slots with non-powers of 2 samples in them, but it has to be done by combining Cooley-Tukey with other forms of FFT. In this case, k starts at 0 and climbs up to 7, except, of course, it only climbs from 0 to 3, as values of k from 4 to 7 aren't needed. The pattern is that n starts at 2 and doubles with every stage. K starts at 0 for every group of butterflies and goes up as far as 1 less than half of n. If there had been another stage, i.e. we had started with 16 sample values, then this stage 3 would only comprise half of those values. There will be another set, just like this one underneath it. After those there will be a new final stage, with 8 butterflies crisscrossing each other. N would have the value 16, K would go up from 0 to 7, not 15, and I would run out of colours in Microsoft Paint. So, there you have it. Now I appreciate that there is one hell of an understanding gap between that and that. So if you only take one thing away from this talk, apart from what a wonderful lecturer I am, then let it be the butterfly method for crashing through the Fourier transform. After all, as I said, many lectures on this subject at universities skip the maths altogether, but rather than simply say, follow this procedure, I think some grounding in the maths helps. One thing's for certain, this is crying out for an example written in JavaScript, don't you think? Watch this space, folks.